Since the beginning of this mechanics series, we've explored how the dimension of mass helps us make sense of space, time, and motion. We then formalized this relationship by introducing mechanical or mass-carrying quantities, especially the standard ones summarized in this table. Initially, we focused on pairs. Pairs in the mechanical plane are associated with power laws in the kinematic plane. The mechanical quantities provide a dynamical understanding of the power law. For instance, in the canonical perspective of a length versus a time, we know how to systematically connect the perfactor and exponent of the power law to the underlying mechanical quantities. Like any power law, this one is apparently self-similar, extending to arbitrarily small and large scales. Apparently, this regime has no preferred scale, but in fact we saw in episode 8 that by choosing the appropriate perspective, the right angle, the constant variable on the vertical axis acquires an objective unit, the constant mechanical ratio. However, the horizontal axis remains without scale. It could have any arbitrary unit, and it could even be any variable of our choosing, beyond powers of the constant variable. Even with the right angle, the power law remains apparently self-similar along this horizontal axis. However, in episodes 9, 10, and 11, we've seen that considering a third mechanical quantity could resolve this issue. As long as the three quantities were not aligned, we saw that they led to three regimes intersecting at a common point, a proper event. The coordinates of such event were given directly by dimensional analysis, and they could be used as objective units for both axes of the kinematic plane, regardless of the perspective. With metric, imperial, or any arbitrary units, subjective units, dynamics pertaining to the same mechanical trio, would appear all over the place. But this mess was not inherent to the phenomenon. It was due to us, to our willingness to impose the same standards, the same units to all. It was due to the mistaken assumption that measurements should be absolute. If instead we recognized the turning points of the dynamics, the events, as the sole natural reference, then everything suddenly looked much simpler. We've seen how mechanics provides objective units, and it is now time to discuss how mechanics can free us from an even more pervasive bias, our arbitrary choice of number base. From the beginning of this series, we've been subserviently using base 10. Why 10? Because of the number of our fingers. But our fingers are no more legitimate than our feet to quantify the world around us. To reach a deeper understanding of the connections between mechanics and kinematics, we must progressively move past subjective standards to measure and to count. We must grow up from our childish finger counting. Although the construction of simple dimensionless numbers, and more generally of objective units, has been the focus of dimensional analysis for over a century, the number base itself has remained largely unchallenged. It seems that natural scientists did not dare touch on this subject, presumably reserved to mathematicians. But we'll see that numbers, just like units, are actually closely connected to the dynamics at play. We've presented this idea in episode 7 of the mini-series on explosions, from a fully mechanical point of view, and we've offered a strictly kinematic take on it in a recent paper. Today we are going to do a little bit of both. We'll start with kinematics and consider how to build an objective base for explosions. We've seen this example several times already. It is the blast radius of Trinity, the first nuclear explosion. We've seen in the last episode that the dynamics are initially governed by the yield and the ejected mass, then by the yield and the density of the swept up ambient air, and finally by the air density and its bulk modulus. Considering these four mechanical quantities, we saw that the full template of the dynamics should include more regimes associated with all possible pairs, 6 in total. But we do not need this mechanical insight to illustrate our point today. Considering these 3 regimes is enough. We do not need to know the mechanics. We may simply say that the initial regime has a constant speed c0, the ejection speed. The last regime has a speed cs, the speed of sound, and the intermediate regime is a 2/5 scaling with a prefactor k. Even with this purely kinematic description, we can identify the coordinates of the 2 points of intersection. We have 2 points, and so we a priori have 2 competing systems of units. However, and it's the catch, these 2 systems of units are related. We can go from the length scale of the first crossover to the second by multiplying by the ratio of speeds raised to the power 2/3. And we can go from the first to the second time by multiplying by the same ratio raised to the power 5/3. This ratio of speeds is none other than the index of these dynamics, written in one of its possible kinematic disguises. We can write it as a ratio of speeds, as a ratio of lengths, as a ratio of times. And when the mechanical roots are revealed, the index can be written as a ratio of the 4 mechanical quantities of the domain, as seen in the previous episode. To be precise, it is the square root of the number we defined in the last episode. But that's just a matter of convention, since we recall that dimensionless numbers are defined modulo an overall power. Anyway, we do not need such mechanical insight for now. The ratio of speeds is enough. Let's return to the data. Right now the plot uses conventional yet subjective units, meters and seconds, and the base of the log is the good old 10. Let's rescale the units first. We have 2 choices. We can use the early intersection or the late intersection. Let's start there. If we use the coordinates of this point as our units, then the coordinates of the intersection naturally become trivial. What is more interesting are the coordinates of the other intersection. A size of 0.022 in units of d star. So the radius of the blast at the late intersection is around 45 times bigger. That is 1 over 0.022. The time is 7.1 times 10 to the minus 5 in units of t star. These numbers are not trivial. Actually, they look pretty random. In fact, they are not. These numbers look arbitrary because we are writing them improperly. There are many ways to write a single number. For instance, the time is written using the scientific notation. We could also write the size with the same convention. This kind of representation has many virtues, but in this context, it is really not optimum. The weirdly spaced minor ticks on the axis of the plot are there to facilitate the translation of values, according to this scientific convention. For instance, 2.2 times 10 to the minus 2 falls near the minor tick 2 above the decade minus 2. These log scales with major and minor ticks are quite common, so we don't really realize how strange they are, but they mix log and linear scales in a convoluted way. Let's get rid of the minor ticks and keep only the major ticks, which have the decency to be spaced regularly. Taking a look again at the size, we can take out our standard ruler, linear, and decimal, and note that the length falls between tick 6 and 7, around 6.6. What this means is that the value of the size can be expressed as 10 to the power minus 1.66. Similarly, the time can be written as 10 to the power minus 4.15. We can also present the plot in this way. This representation is valid, but now the logs, minus 1.66 and minus 4.15, appear random. The values depend on the choice of base 10. If, for instance, we were to choose base 2, then the values would change accordingly. Is there a preferred base where the logs would take more sensible values? Yes! Of course, we know what it is. We've seen that we can express the coordinates of the early intersections as powers of the index. No need to split hairs. We have our base. In log n, the coordinates of the intersection are now quite comprehensible. The numbers are rational and they come directly from the exponents of the regimes. If we prefer integers rather than fractions, we can use base n to the power 1/3, since anyway the index is defined modulo an overall power. With this base, the coordinates of the early intersection are now simple, minus 2 and -5. Numbers that are quite natural since the intermediate regime has a slope of 2/5. The result of using this base is so simple that for future reference, we will introduce the symbol R to refer to it. R for radix, which is another name for base. All these changes of variables may seem a bit silly when we only have a single dataset, but they make a lot of sense when dealing with a bunch of experiments. The Trinity test is up there. It was a bomb detonated on top of a tower. The other datasets correspond to a vast range of explosions, nuclear, conventional, and induced by lasers, in the air and other gases, or underwater. We provide much more details in the explosion series, and references to the original studies are given in the video description. Not all datasets are complete, some showing only the early part or the late part of the dynamics. When they are represented in subjective units, here the meter and second, these datasets do not seem to be particularly congruent. On a plot like this, it's hard to believe that a huge nuclear blast has anything to do with a tiny laser-induced ablation. The situation changes if we modify the units in such a way that the coordinates of the late intersections are used for all datasets. As the units change, the curves are translated in the log plot. Then all late and intermediate regimes overlap, since they intersect at the point we've chosen to set the units. But the early regimes do not overlap. The larger the value of the index, the further the initial regime is from the late intersection. If to set our units we were to choose the early point of intersection instead, then all initial and intermediate regimes would overlap, but the late regimes would not. It's almost sad. We have two competing systems of units. In each system, one of the regimes is sacrificed. Data along this regime cannot be overlapped. However, this unfortunate situation is not inescapable. This conflict is not inherent to the phenomenon. It is due to us. It is due to our willingness to impose the same standards. The same base tend to both plots. Selecting objective units is an important first step, but we need to go all the way and pick an objective radix, an objective base constructed from the value of the index in each experiment. Then the two plots are essentially identical. The log coordinates are simply shifted by constants. When units and base are selected objectively, rather than based on arbitrary conventions, then all dynamics overlap, on the early, intermediate, and late regimes. The overlap only fails in the vicinity of intersections. In the neighborhood of events, we'll come back to that in a few episodes. Whereas a change of coordinates has the effect of translating the curves in log space, changing the base dilate or contract the curves so they can eventually fit together. In the end, this universal plot is much more easy to understand than the plot we started with, where the similarity between the dynamics was hard to believe. However, this plot and this one contain the same data. The only thing we've done was to systematically remove our footprints and our fingerprints from the canvas, to select objective units and an objective base. If the initial situation was messy, it was not because nature is messy, but because we blindly relied on arbitrary, subjective conventions. Explosions do not comply to our standards. When represented objectively, all these explosions are similar, they follow the same path. This is in fact the case as long as the index is greater than 1, as long as the explosions are detonations, as discussed in the previous episode and in the explosion series. When n is smaller than 1, for deflagrations, the dynamics follow a different path. We don't have much data on deflagration, so let's move to drops and bubbles to get a better feel for this duality once an objective base is selected. We've seen in the last episode that to study the pinching, spreading, and coalescence of droplets and bubbles, considering that the mechanics were due to a surface tension, a capillary force, a density, and a viscosity was a rather good idea. By computing the regimes associated with the 6 pairs from this set, we saw that we obtained a domain looking like this in the canonical perspective. To be more precise, The domain looked like this when the index was greater than 1, and it was flipped on its head when the index was smaller than 1. In this context, the index was the Laplace number, although as usual powers of this number are equally good. Before we consider the full domain, let's focus on only half of it. These regimes still require the full set of 4 parameters to be described mechanically. Since the linear regime is viscocapillary, the 2/3 regime is inertia capillary, and the constant size combines surface tension and capillary force. We've seen these regimes a bunch of times already. As with explosions, we actually don't need to dwell on the mechanics to work out an objective base. We can simply call the constant size capital D the speed of the linear regime c, and the prefactor of the 2/3 regime k. We have 3 kinematic parameters. We can express the index from these 3 parameters. We can also express the coordinates of the 3 points of intersection using the kinematic parameters. The first point depends on k and c. The second point depends on d and c. And the third point depends on d and k. Nothing surprising here. In the case of explosions, we only had 2 intersections. Because 2 regimes were parallel, here we have 3. But the coordinates are still connected by the index. As in the case of explosions, we can pick any one of the 3 systems of units, and then use the index as radix. To illustrate this rescaling, we can consider the data on spreading, pinching, and coalescence that we've already seen a few times in this series. In subjective units and base, using meters, seconds, and the conventional 10 as radix, all these datasets crisscross each other in a tremendous mess. However, if we use the coordinates of the intersections to craft our units, the data organize much more nicely. This is the pattern we get when using the first intersection between the linear and 2/3 regimes. This is what we get with the second intersection between the linear and constant regimes. And this is the third between the 2/3 and constant regime. Each system of unit favors 2 out of 3 regimes. The dynamics look quite different in these 3 systems of units, but it is only because we are imposing base 10. If instead we use the index as our base, we get a universal plot synthesizing decades of research. There are a few things to unpack from this figure. Let's proceed step by step. First, this plot uses the coordinates of the first intersection as units, but using the second or the third does not change the pattern, it only shifts the coordinates. Which one of the 3 system of units we choose doesn't matter much. Another thing that can be adjusted without major impact is the exponent of the index. Here, the index is the number n we defined earlier from the 3 kinematic parameters. Each experiment is associated with a value of n, which is color-coded. With this index, some of the ticks on the horizontal and vertical axis are fractional. We can get rid of those ticks if we favor integer exponents. Alternatively, we can define an equally valid radix by taking the square root of our initial index. Then all ticks are neatly integers. These are really details. The most important thing on this plot is that it displays 2 paths. Close to the turning points, the exact value of the index seems to matter. The closer the index is from 1, the smoother the transition. We've seen this already for explosions, and we'll return to it in a few episodes. If we neglect this subtlety for now, the shades of blue and the shades of red do not really matter. There seems to be only 2 colors. When n is greater than 1, or equivalently, when the radix r is greater than 1, the order of the horizontal axis, and of the vertical axis follow the tradition of increasing from left to right and from bottom to top. R square is greater than r, which is greater than 1, etc. In contrast, when the index or radix is smaller than 1, the ordering is reversed. Instead of starting at the bottom left corner of the image, the dynamics come from the top right corner. The 2 paths occupy 2 distinct regions of the little piece of space-time, delineated by the 3 intersecting regimes. In this objective representation, with objective units and an objective base, the duality of the domain that we introduced in the previous episode is manifesting itself quite strikingly. The origin along one path becomes the infinite along the other, and vice versa. Maybe some of you have already noticed that the structure of this kind of plot feels a bit like a projective space. But we'll have to wait for a future series to dive into that, and to see how path selection might be looked at from that angle. Earlier we said that decreasing the index below 1 would flip this little triangle of spacetime. This is still true, but there are several ways to represent such transformation. We can rotate the drawing by 180 degrees, while keeping the orientation of the screen fixed. Or we can keep the drawing and flip the orientation. If the base is fixed, for instance chosen to be the conventional 10, the duality between indices larger and smaller than 1 can also be visualized in each one of the three objective systems of units. Here with units 1, only the constant regime changes as the index varies. The duality takes a slightly different look when using units 2. And here with units 3. With an objective base, the triangular piece of spacetime stays unchanged, and the emphasis is on the associated flows. In this objective plot, the focus comes back to the problem of path selection across a domain of interconnected events. Why are these paths followed and not others? Well, other paths can actually be followed once we recover the 6 regimes of this domain. 6 regimes from 4 mechanical quantities. We can recall some of things we've learned in the past episodes. So far today, we've selected experiments following this path when the index is larger than 1, and this one when the index is lower than 1. But other paths are possible. For instance, this one, what we called Rayleigh's regime in episode 10, combining force and density. Also, in episode 10, we introduced this regime, combining force and viscosity, and relevant to the coalescence of droplets and bubbles in significantly viscous outer fluids. Multiple paths are possible for large or small values of the index. Experiments have shown this quite clearly, in particular for large values of the index, that is large Laplace number or small Ohnesorge number, where Rayleigh's regime provides an alternate route to the inertia capillary regime. Experiments are clear, but the mechanism of path selection is not yet understood. We hope we've convinced you that an objective plot like this puts us in a better position to understand these dynamics than with the subjective plot we started with. We've devoted several years to collect and collate all these datasets, revealing their underlying template. Similar objective plots can be built by analyzing sets of dynamics associated with different quartets of mechanical quantities. We'll discuss the kinds of domain topologies we can get in the next episode. We'll see that the number and type of events, the topology, depends on the relative positions of the mechanical quantities in the mechanical plane. Once the mechanical quantities are known, their domain of influence is also determined, and the objective units and the objective base can then be expressed in terms of these mechanical quantities. What we also saw today is that an objective representation can actually be achieved when the mechanics are not yet known. Units and base can be defined kinematically. Before moving on to the next episode and to these pretty patterns, we can conclude what we've done today by saying a few words about what we may call triads. The four triads. The 4 ways 3 lines can coexist in the kinematic plane. The 3 lines can intersect at the same point. We've called that a proper event since episode 9. The angles of the lines depend on the underlying mechanics and on the choice of kinematic perspective. The 3 lines can also be parallel, as first discussed in episode 12 and more generally in episode 13. Different spacings are possible. Today we focused on the first 2 triads, the parallel case for explosions, the triangle for droplets and bubbles. We call these 4 patterns triads, rather than trios since we've reserved the term trio to sets of three mechanical quantities. The relationship between triads and the mechanical plane is not trivial. The three kinematic parallels can be encoded by an aligned mechanical trio. The proper events can be encoded by non-aligned trios. The other two triads require at least 4 mechanical quantities. With what we saw today, we can add that these 4 triads also offer ways to move past subjective standards, to measure and to count. The triple intersection provides objective units for both axes of the kinematic plane, regardless of the perspective. In contrast with parallel lines, we could only get 3 competing units for a single axis, the right angle, but we got an index and so a base for the constant variable, an index that can be used to express the 3 competing units. This base was connected to the relative spacing of the lines. Finally, with the last 2 triads, we have both units and a base. Plotting a single power law requires a choice of units and a choice of base, choices that are made subjectively, solely guided by arbitrary conventions, be them national or international. In a plot like this one, or this one, the human presence is everywhere. Our feet are used to measure space, our hands to count. The unit of time is barely less biased, a mixture of Egyptian and Babylonian fractions of the rotational period of our own planet. These provincial choices are required to describe the phenomenon, but the phenomenon itself is expected to be independent of these choices. More important, this independence can only be reconquered if the phenomenon is not as simple as initially thought, if the dynamics show at least 3 connected trends, rather than a single power law, either delineating a triangular piece of space-time or joining 2 parallels. This inherent connection between the wondrous diversity of nature and the objective description of phenomena reveals a key insight. Simplicity, as appealing as it may seem, often obscures the underlying richness of the world. A phenomenon that can be described by a single power law is inherently tied to the subjective choices of the observer choices that impose our human scales and perspectives onto the data. In contrast, when we encounter a phenomenon characterized by multiple, connected power laws, we are granted the opportunity to strip away this human imprint. The units and base used in our descriptions become dictated by the data themselves, reflecting the true nature of the phenomenon rather than our conventions. It is important to distinguish, however, between the objective diversity of nature and mere complexity. Consider these 2 subjective plots for explosions, and for drops and bubbles. Multiple datasets, gathered under varying conditions, are plotted subjectively, with meters in second and 10 as the base. In both cases, the result is a tangled jumble of data points that seems overwhelmingly complex. This apparent complexity, however, is often a reflection of our arbitrary choices in units and base rather than the phenomenon itself. When these units and bases are determined objectively, the data align in a more coherent and understandable pattern. By removing the subjective layers, we unveil a clearer, more interpretable representation of the underlying phenomena. What once appeared as a convoluted mess now reveals a pattern free from the distortions of human perspective. Once they are stripped from our footprints and fingerprints, the data are ready to be interpreted. This interpretation does not rely on our measuring and reckoning conventions anymore. Instead, it invokes mechanics, which completes the picture and can reveal all through this web of space and time. A web that we will try to better understand in the next episode.